this video, we want to build the best PV system for the house. Now, before undertaking any PV project, we need to know the following: the shading, the tilt angle, the sun hours, and also the safety and security for the system. On the first point, when designing a PV system, one must investigate how the following will affect power output: the shade from the neighboring trees and buildings, cloud weather, and shade from adjacent solar panels, especially if they're on a mounting. The point number 2, the module's tilt angle to the horizontal is critical as to how much radiation will be directed normal to the panel. This is calculated from the latitude of the location where you are installing the system, or alternatively as dictated by the pitch of your roof. In this section, we are looking at how to set up the tilt angle and the azimuth angle. The tilt angle is based on this equation, and if we look at this diagram, we can try to rotate the module to show both the tilt angle and the azimuth angle. So I start with the tilt angle, and that one is, if I use this protractor to demonstrate the tilt angle, it is the point, it is that angle between the horizontal and the vertical tip of the module. As you can see there, that should give us the tilt angle. And from the equation that we've just shown, you will be able to calculate based on your latitude where you are, and that will give you the tilt angle of the module. But this will be useful if you are doing a new module mounting. Otherwise, the pitch of your roof will already fix. Unless you put a mounting on the roof, the pitch of the roof will already fix how the vertical or the inclination of the module is going to be. If we look at the azimuth is the horizontal angle from the north, and it is measured based on your magnetic compass direction from the north. So that angle, the dotted line, giving us the clockwise movement from the north to south, that angle is what you measure as your azimuth. And by using a magnetic compass or a mobile app, you can be able to measure the azimuth. So it is just that simple. It's not a complicated thing. So once you have the right tools, then you can be able to determine the two angles that are required for setting your PV module for maximum solar irradiation collection. So we move back to the design. The third point is the sun hours. The critical thing about the sun hours is the lowest irradiance that will be required to generate the needed output. What happens is during the year, it is required to know the month with the lowest sun hours, and this is what is used as the basis for the design. For safety and security, it is required to observe personal safety during installation and security for the modules if the site is to be accessed by unauthorized persons. The other aspects that you need to observe during the site assessment include aesthetics, accessibility, roofing material strength, and the structure. And this is for a roof PV system, because as you realize, if you will be stepping on the roof, then you need to take caution so that the roof is preserved during the installation. So there are 3 types of PV systems that are of interest to us. We start off with the off-grid system, and as the name suggests, this system is not connected to the grid. So we solely rely on the PV supply in order to charge our batteries. Then during the day, the battery is being charged. Then part of that power, if it is in excess, can go to serve the electrical components in the house. At night, because there's no more charging of the batteries from the PV, the stored power goes to the inverter to generate AC for the electrical households. So should it happen that the power is not enough, then we are likely to have a blackout. So that is one unique thing with the off-grid system. Next, we look at the on-grid system, and in this system the supply is generated from two sides. One side is the PV system, which generates power to the inverter, then it serves the household components. Then if there is excess, then it is passed on through the bidirectional meter, then to the grid. Otherwise, if there is no excess power, then there is likely power to come from the grid to supplement what the PV is producing. So at night, because there is no sun, the PVs are not generating power, so the only power should be from the grid. In the hybrid system, we are having a combination of both the off-grid and on-grid modes. So this particular system, what will happen during the day is that we will have it like the off-grid, where the PV will be charging the batteries and storing energy, and the excess energy will go to serve the electrical appliances in the household. Then the excess will pass through the utility meter and onto the grid. So that's during the day. At night things changes because there's no more charging with the PV panels. The only power now comes from the battery, and it serves the electrical appliances, and if there's a shortfall, the shortfall is met by the utility side or the utility supply. In the off-grid mode, the utility now is not connected, and then we are having now during the day the PV panels charges a battery, and there is interaction both forward and backward, because if there is enough power, then the batteries are charged, and if it happens that there is a shortfall during demanded by the electrical appliances, then that power comes from the battery. If it happens that the power is not enough, the off-grid mode will lead to a blackout, because there will be no power from other sources since the grid is disconnected. So in this mode, as the name says, it is working just like the off-grid that we have seen earlier. The best thing with the hybrid system is that then you have both the on-grid and off-grid system put together to give you the benefit of the supply from the PV during the day, and at night you can meet your shortfall from the utility side or from the grid side. And if you so wish, you can switch off the grid and then remain with the off-grid mode. So we want to look at the comparison between these three systems, just to understand and help us decide which system suit our needs. So we start with the off-grid system, and these are some of the key points that we have here. Because you are not connected to the grid, then it eliminates that cost. There are no bills because power is produced and being stored in your battery system. The main disadvantage of this system is that it requires batteries which needs to be replaced after 10 years. That is the life period of some of the common batteries. Then other points is that we need this equipment here. We need modules, we need disconnect switches, an inverter charger, a battery bank, and in some cases a backup generator. Of course, this is probably may not be required, but at times it may happen that the battery goes low and maybe the sun is not there to recharge. Then you may need something to supply power to the system, because already we are off-grid and there's no line connected to our system. The next system that we look at is the on-grid system, and we just look at the key points. Then we are saying that there's no need for the battery bank, because the grid will act as a virtual batteries, because you're just producing power and you're sending it to the grid. And some of the things that we need to look at here is the grid tie inverter, and we will require the kilowatt meter that will monitor what you're producing, and also for the grid company also their meter which will monitor what they are feeding into our system. The third system that we talked about, or that we listed there, was the hybrid system. So the hybrid system is a combination between on and off grid and has characteristics of both systems. The system can be set such that the PV power is exhausted before the grid is connected. So that is a setting you put in the inverter, which will dictate when the power from the grid will enter into your house system. So the battery provides a backup when the grid goes off and ensure an uninterrupted power supply. And as you have seen from this discussion, the hybrid system gives both worlds of on and off grid system. So this is a system that we are going to design for our home using the PVsyst software. So when you open PVsyst for the first time, this is a screen that greets you. And here there are several menus, and the one that is key to us is this one, which is open here, and it gives us the option to design what we want. There is a grid connected, then there is a standalone, there is a for pumping system, and of course databases and tools for the software. Now what we are interested in is the grid connected. However, the grid connected, when you add the loads to it, because it has the option for adding loads, then it becomes the hybrid system, which now has a component for supplying the excess power to the grid, but most of it is used in the house. So I'll click that one, then it opens this page, and I'll need to add in our project name. Say we call it hybrid home system. Then it is a new site, so it needs to get the meteor data for the site. And what I'll do is to click this button here. Then this page opens up, and it is asking us to give it the locality where we are going to do the design. So I'll give it the coordinates of the site. I'll put in the coordinates. So I'll tell it to search. So one thing though, you need to have a good internet connection for it to be able to perform this function. So you can see it has brought us here to a town called Narok in Kenya. Then I'll accept the selected point, then it wants me to put in a name. Let me just call it as the name of the town. Then I'll tell it to get the data from, because we are looking for the data, so I'll tell it to get from the coordinates, and we click that. So it needs me to define the country, so of course I'll select the country is in Kenya. Then once I do that, this part opens up to allow us to import the monthly meteor data, and we are getting it from Meteonom. So I'll click import. So having good connection is very important. So you can see it has brought for me this data for the site. This is a global horizontal irradiation, which we need, which will tell us the hours, the sun hours. So instead of this highlighted one, I'll pick on this one for the day, not for the month. Then with that, I'll accept this data, click OK. Then I'll save it. The dialog here is the geographical site file Narok Township is now saved in the database. I'll say OK. Then accept this one. So this is saved. Then the data is now into the system. So from here, it wants us to selected Narok file, please save project. So I'll save the project. So once it has saved, it opens up this page, which is where the main design is going to take place based on the following tabs going around. And then eventually it will open the simulation part. So the first part, or the first thing to do, is to do the orientation. And here we supply the details of our roof, because this is going to be on the roof, and our pitch is 22.5. The azimuth is 0 because we are in the south, so I'll accept that. So you can see the orientation has turned green. Then I go to the system, and the system here we need to supply the planned power. Then we'll select the modules, then we select the inverter, then the other information it will process. So let's start by giving our planned power. So I'm going to put about 1.8 kilowatt. Then we need the PV2 modules to supply that power. So I'll select, okay, it has selected Jinko Power, so I'll go by that Jinko Power. There are others though in the list. As you can see, there's quite a number in the list. Then we select the Jinko that you're looking for. Now to get 1.8, I'll go for a Jinko of 300 watts. So 300 watts is here. Then I think that is okay. So it is seen that we are going to use 6 modules to get, of course, 1.8 kilowatt. Then we give it the inverter now. So here we look for the inverter, and the one I want to use is, yeah, this one, Victronic Power. That is a company name. Yes, and this inverter was not in the database. I've just put it. So if you don't find the inverter you're looking for, because this is where the main design is, by just selecting any inverter, you will not know the characteristic of that inverter. You need to have its data sheet so that you can be sure that the inverter you are looking for is the right one that you're putting for the design. Because the inverter that we are using now, this Victronic Power, and with that model there, Infinisolar. Now this inverter, if we see the data sheet, so if we look at the data sheet of the inverter, you will see that this is a grid tie inverter, but with very specific functions. So there is this part of self-consumption and feeding into the grid. This part is very important, and also there is the part of the charging of the battery, so that it has, you're using the power for self-consumption, but also the excess is fed into the grid. This is a unique part of this inverter. You can of course use other inverters and combine it with a charger controller, so that you have now 2 electronic devices there, the controller and the inverter, to give you this functionality that is on this single inverter. So that is why I've selected this inverter, to be able to take us through this design. Also, some of the notable features of this inverter, if we just scroll down on the datasheet, we see the voltage nominal and the maximum it can take per string. Then what we'll use immediately is the battery charger, and that it is a 48 volt VDC. So we shall see this when we are selecting the battery for the storage. So we go back to PVsyst and continue with the design. So our inverter, as explained, is there, Victronic power, and there is no error. Otherwise there would be an error here. Like for example, if I picked say another one, you see something like the inverter power is strongly oversized, because you can see that this is a 10 kilowatt AC inverter here, but our Victron power is 1.5 AC. So, and you can see the power you're putting in is 1.8. So this is a very good DC AC ratio. So if we look here, we see that it is saying that it will have 5 modules in series, although we have 6. For us to be able to have this power, I think I'll push it up and slightly overpower the system, so that we have, still there's no error here. So we continue with 6 modules in series and 1 string. On this side I think everything is okay, so let's proceed. Then the system is set. We are still not going to run the simulation because we still have all this to do. So let me go to detailed losses, and I'll not interfere with this. I'll come here to ohmic losses and maybe do detailed computation, and this is to do with the power loss in the cables. What you need to do is check here as I feed in the values here. So string module connection, this is from the roof going into where the inverter will be placed, maybe inside the house or somewhere outside, just under the roof. So I'll give it maybe 15 meters or maybe 20 meters max. Alright, then there's the resistance, and main box to inverter, this is a short distance, maybe just 5 meters, right? And there it is. So looking at this, global array resistance is 150 ohms. Then we can see the losses here at about 0.9%. So let us look at the sketch. That is a sketch, and this is what we are looking at. Let's go to the target loss fraction. This one you can put in this most of the time I'll put here 2%. Then we look at the wires, and the wires I think are done a design earlier, and this is just estimation of the wire prices. So this is just okay. I move on to the next stage. Ohmic losses, module quality, I'll not touch that. Soiling loss, maybe I need to put something here because after all these things will be dirty and so on, so I'll take on the default value they have. Then other losses, I'll leave them as they are. So I think we are done with that section. I'll say okay. Self-consumption. Now this is as you've seen it, the inverter has it is taking to the grid, but it has the part for self-consumption. That self-consumption means that the power is producing will first of all be used in the household before it's taken to the grid. So I'll click on this one, and we need to define the usage of the items in the house that are going to use power. So I'll click on this household consumers. Those are the items in the house, and when you click that, this screen comes here. Always you look at this blue screen here to tell you error messages or what you need to do. So here it is telling us we have not defined, so please press household use, which is this one here, and when I click on that, it opens up this table where I am supposed to fill the items or the electrical loads in the house. So if I start with this one, these are lamps, so I'll put like about 5 lamps. These are lamps in the house, and when I click on that, it opens up. So the power that each lamp uses is 10 watts. Then I have one TV using about 150 watts. That is TV 150 watts. Then another item is the laptop, one laptop, and then I give it 120 watts. I come to the fridge, one fridge, and maybe give it 2.5 kilowatt per day. I don't have a dishwasher. So other thing, I can put in 4 security lamps. Using about 10 watts each, as in the first case. Then other uses, miscellaneous electrical items in the house using power, so I'll give them about 100 watts. So if you have other things, either you can group them or combine. You can group them if the space is not enough. So look here that there's only one which has been okayed. The others we need to specify the hours, and once we do that, then they'll all turn green to show that they've been set. So to do that, you click on this hourly distribution, and we start with the lamps. The lamps, we are going to do 5 hours, and that is maybe from 6 there, and we go on putting on the hours until we get the 5 hours. The TV also, maybe some small news catching up, and then we go like that. The main part, of course, is in the evening. So if you have overdone it, you right click. Now to add, you left click. So like this one, if I want to remove this one, then I right click. If I want to return it back, if I want to remove, I right click. If I want to add, I left click. So our 5 hours there is done. Then we come to the laptop, so we start with it somewhere in the morning. There we are catching up with mails and so on, chatting up with friends, and it continues like that until we get our 5 hours. Or maybe let me use it for 8 hours, add in some time, yes, so that we can use it for 8 hours. Something like that. Then we move on to the security lamps, and these have said they will be on till close to the wee hours of the morning. So we go and continue like that up to maybe, yeah, up to 5:30 there. Now if you don't see something, you move this thing here so as to show you all the items that you have. So you can see like the other uses was hidden somewhere, So now it has come out, so I'll fill it. So other uses also for 5 hours, and these are small items using electricity in the house, charging phone, maybe the blender, and so on. Right, so that one is done. So I think all of them are done. So if you want to be sure that you've done, go back to the consumption and you can now see everything is okay. So we are done with the consumption. I'll tick OK. The message here is a self-consumption with an average of 5.38 kilowatt hour per day has been defined. So this is okay. So you can see the self-consumption is now highlighted. So there's an issue of the storage, and let's go to the storage, and please choose a storage strategy. So what do we want to do? We want storage for self-consumption, alright, and when you do that, it opens up the battery. For you to select the battery, the consumption is what we have already told it. You cannot see that it has already picked it. If I click on it, it will show us what I've done before. Yeah, we were here before, so let me just cancel that. Then here we are supposed to select the battery. So before I can select the battery, we need to know the system ampere hours so that we can decide how many batteries we are going to use. And for me to be able to do that, I'll step out here so that we can look at a presentation of how to determine the system battery. So in order to calculate our battery requirements, we are going to use this equation here, and it states that the system ampere hours is given by the daily consumption times the days of autonomy, meaning that those are the days you'd want. If the system is down, then you still have power from a battery, then divided by the system voltage times the depth of discharge times the inverter efficiency times the battery derating. So that gives us the battery size of the system. Now if we look at what we have already calculated, we already have the daily consumption as 5380 watt hours per day. Then the system voltage from that inverter, the inverter system voltage is 48 volts VDC. Then the days of autonomy, we want that we can be 1 day, full day without power. If I wanted maybe 2 days, then but that will affect the cost of the, will increase the cost of the batteries. And the depth of discharge is how much do you want the batteries to be drained before recharging takes on. So we want it at 50%. Then we have the inverter efficiency. Then because of temperature affecting the battery system or the battery cells, then we have to adjust that, and we derate the batteries by 5%, meaning that they're operating at 95% efficiency. So that is the equation. When you put in the figures, we see that we will get the system ampere hours as 248.4, and that approximates to about 300 ampere hours. So the batteries that can work with this system is 12 volt at 150 ampere hours. So to know the number of batteries in series, we take the system voltage divided by our battery size here, and that gives us 4 batteries in series to get 48 volts. Then we look at the number of batteries in parallel, or the strings. This is given by the system ampere hours, which we have calculated at 300, divided by the ampere hours of the battery. So we have 2 strings. meaning that we have now 4 batteries in series times 2 strings. So there we are, we have finished that calculation. We go back to PVSys to continue with our design. So we have gone through that battery selection presentation. Now let us put that information here in PVSys. And if we open here, this one gives you the names of companies that are making batteries. And there's a technology, so I'll choose lead acid. Then when I do that, from this company they have a list of batteries that one can select from. So the battery that we've selected is a 12 volt 150 ampere hours, and it is this one here. Then we have seen that we need 4 batteries in series so that we get 48 volts. So I'll put that one. So 48 volts. And then we need 2 in parallel, which gives us 300 ampere hours. So our setting here is done with those configuration there. Yes. And what you need to know also is, if you look down here, you'll see that the system charging time during full sun condition is 6.4 hours. The discharge under average load is 51.4 hours, which is slightly over 2 days. So we are okay. I'll accept this configuration. Then please define maximum charging time. Do you want to know? So let's define that. Let's define the charging time. If we come here, the maximum charging time is about maximum charging power is about 1.6. That is what it was asking. So I think I'll just leave it like that, so that it uses power to charge and then store it in the battery. Alright, so I'll just tick OK. Then it is ready for simulation. Now see that all this now have been turned on. I will not do the horizon and also maybe near shading. I think let's click energy management. We see what is there. And this is power limitation. I will not go into that. Then also please run the simulation first. So I think I'll do this one afterwards. Maybe it will give us the information then. At this point I'm ready to run the simulation. So I'll click on run. Then it will go through the information, processing different information to give us the results. So these are the results. Various tables are under here. If you look at this, a lot of information here. You can choose the table that you want to show, or the graph that you want to show. That one is already there, and so on. Several graphs are there, but of importance is also this top part here. This is about our project. This is about the information on the modules and the inverter. Then this is about the system production per year, and this is actually the main results. So the report actually is incomplete before doing the economic analysis. So I'll click on the economic analysis. And we need to work out the figures so that we have sort of like a bill of quantities that can be used to analyze the profitability of this system. So I'll start from here. We have 6 PV modules, and I'll put this is about per piece. I'll give, let me change this to dollars. It's easy to work with. So I'll give these ones $100 each. Then module support, these will be fixed on the roof, so maybe I'll spend about say $40. Then we come to the inverter. This inverter, I'll give it about say $400. Of course it could be cheaper than that, but maybe by the time it arrives where I am, it could be that amount. Then the batteries, there are 8, each of them I'll give also $100. For the fasteners, I'll just give a global figure, so one lump sum, then say $30. The wiring also one lump sum, maybe $40. This is not a very big system. Then the combiner box, maybe one at let's say 45 or say 50. Then the monitoring display, maybe just one there, another say $50. Then this measurement I'll not put in, this is a home solar residential thing. Surge arresters, maybe I'll put 2. Let me give them at $50 each. Okay. Now you can put according to your rates. Some of these figures are generic. Then studies and analysis, engineering, a lump sum figure, maybe let me put $150. Permit, say roughly $50. Environmental studies, maybe another $50. And maybe that can include economic analysis. So the installation, a global figure, I'll just use a global figure and say put $150. Transport, a lump sum figure again of say $30. And grid connection, a lump sum figure of let me say $150. That could include maybe the meter or something. Let me increase this to $200. Alright, let me see if there's a cost I need to reduce. Yeah, I'll leave it at that. I'll leave the cost at that point. Then we cross over to this side of maintenance. I'll not be paying any salaries, maybe cleaning of this thing, and say maybe $100 in a year. Then there is the provision for the battery, because after 10 years we need to replace the batteries. So I'll give roughly, we can see that we'll need 8 batteries. So maybe $80 or $90 per year, so that by the 10th year we have about 900. Yes, the others I'm not paying rent, I'm not paying insurance for this thing, although it is good to have insurance money. Okay, I could add in insurance. This is let me say liability insurance, maybe just add $100. Okay, and the rest I'll leave like that. So The maintenance side is 290. The equipment side is 2940. So once you finish with this page, you go to this tab here. So when you come to this page, you will see the following information, and the scripting information is this one here. I'll be using my own funds to do this project, so I'll put in 2940. Then that one now is covered. Then when we look at the tariffs, maybe this one is very high. If I put 0 here, you will see that probably it will say the system is. So depending on your setting, you can put in the values as per your region, and maybe I'll put in maybe $0.3 per kilowatt. Then because we are not being paid this money, what happens is that the power that we produce passing through the bidirectional meter supplied by the utility company. So when we supply power into the grid, the meter works counterclockwise, and when the utility power gets into the system, then it works clockwise. So, or in other words, it works in the reverse direction when we feed in the power to the grid, and it works in the forward direction when we draw power from the grid. So the payback period according to this project is looking like 14.4 years, although that's a very long time, but it is because of the financial area here. If I increase this one maybe to 6, for example, US cents, then you see that one reduces to 6.3. So that is a financial analysis. If you look here, this is the amount of carbon emission, the tons of carbon emission that we will have saved by doing this project. Yes, and I think basically that is a part of the economic analysis. So I'll say OK. Then the next thing is now to look at how the report looks like. So if I click again to generate the report, it should now have the economic analysis included. So this is our report. We can browse through briefly. We start with, that is a cover page. Page 2 is just a project summary and the details of what we've used. This is a table of contents. Then we didn't do shading analysis or near shadings to the building. And this is a array there, and the inverter on this side. So all the information have been captured. This is our consumption, the one we put in the table. And these are more graphs. The global horizontal irradiation. You can see the month of June there with the lowest irradiation. And this is the data from the meteor. So we proceed. Now this is a system loss, how the energy is lost as it comes in. This is what arrives on the panel, and then this one gets off. You can see the soiling loss that we put in there, and eventually at the bottom we are using 1695 kilowatt hour of the produced energy, and 862 is sent to the grid. What else? Those are graphs, more graphs, and this is like our bill of quantities or bill of materials, and you can see this is our total 2940, and part of this can also, of course, these ones affect the profitability of the system. So depending on your costing, some of these cost, if adjusted, then the viability or the break-evening point of the project comes much earlier than the 6.4 that we have seen, the 6.4 years that we have seen. So this is the more financial analysis, page 12, and this is a cumulative cash flow graph. So our break-evening point is there. Yeah, then that is the end of that report. So from here, I think the next thing that we need to look at is the line diagram of the wiring system. So let's move there and have a look at it. So this is a one-line diagram of our installation, and I'll move from left to right, looking at the various system components that we have in the design. So we start with the solar panels, and there are 6 pieces of 300 watts each, all connected in one string in series. Then we have a disconnect switch and a fuse, either fuse or MCB can do. The line is 2 cables, that is a sign there. Then we have our inverter, the Infinisol version 5.2 at 1.5 kilowatt, and as we saw in the data sheet of this inverter, it is an on-grid inverter with energy storage functionality, so meaning that rather than send the power to the grid entirely, it will first of all store that power, because our produced power is cheaper than the power from the grid. So it will produce that power and we store it in the battery, and the batteries are 12 volts 150 Ah, 4 connected in series, and the series are in parallel together. So once the inverter has supplied us with the power and charged the batteries, then the excess power can now be sent to the grid, meaning that the function of is to help us save on the expensive grid power. So we have the inverter, then we have on each side surge protection device, and this is DC side and this is the AC side. Then we have an MCB just to control or protect our system here, and a disconnect switch, so if we don't want to send the power to the grid, then we can put off that switch. Then we have this optional watt meter to monitor what we are producing and sending across. You can either have it or you can leave it out in your design or installation. Then this is where our electrical loads in the house are connected, and it is a consumer unit. Then we have a switch here which just disconnects everything from the system, from the utility side. And this is a bidirectional meter supplied by the utility company, and the way it works is that when we are producing and sending to the grid, then it works in the reverse direction, and when we are getting power from the grid, then it works in the forward direction. So that way we are able to minimize the power coming from the grid whenever we are producing power. Then we have the main protection. This can be the main fuse of the system, protecting us from the utility side. So this is the side of the utility provider on this side of the dotted line. So essentially this is the one-line diagram of the system. And with that, we come to the end of this presentation, and we hope you've enjoyed this design. So thank you, and bye-bye once again.